Hi everyone, we'll solve the third worksheet. So if you have any question, I'll be doing my office hour on Fridays between 5 and 7 p.m. so you can attend these courses. Okay, we start with the third question. We have a drawer which contains a dozen brown socks and dozen black socks. We want to compute this part. So how can this man who takes out the socks, how can he be sure that he has at least two socks of the same color? As there are 12 brown and 12 black socks, if he takes out the 13 socks, he'll know at least two of them are of the same color because there are 12 brown socks and 12 black socks. Okay, so the last sock, okay, the 13th sock will be either brown or black. So, and previous one should contain either brown or black sock. So the number is 13 for this part. And what about B? We need to compute this, or we need to think about this. Now we want that he has at least two black socks. Okay, we have 12 here black socks and 12 brown socks. What do we do for that? At least two black socks. So the answer is 14. Why? Because there are 12 brown socks and 12 black socks. If the man takes out 14 socks, we know there are 12 brown socks, so we have plus 2. These cannot be brown socks, okay? If they were brown, these two cannot be brown too because there are 12 though, okay, 12 of them. So these two will be black socks, okay? So the answer for that is 40, okay? Now we have this question 5, okay? I followed the same worksheet, but I wrote the questions here too. So the question is this. We have first 8 positive integers, okay? Here we have. And the 5 integers will be selected, okay, from these ones, okay? Now we want to show that there must be a pair of these integers, from these 5 integers, with a sum equal to 9. So here we have these 8 integers, okay? Now remark that we have these pairs whose sum is 9, okay? We have these 4 pairs. As we want to select 5 of them, okay, 5 of them, and as there are already 4 pairs, now this 5th one will give us one of the one of the remaining pairs, okay? For example, if we chose 1, 2, 3, and 4, then the 5th one, the 5th number, will be one of these pairs, okay? So at the end, we'll have a pair, okay, whose sum is 9. So what about B? It's enough to give a counterexample. So if we select these 4 numbers, we see that we don't have a pair whose sum is 9. So this is a counterexample for this part. So it's not true. Now we want to compute the number of bit strings of length 10, which contain exactly 4 ones. Now, how do we compute it? So we have 10 digits. Okay, and 4 of them, for example, this, and this, okay, 4 of them will be exactly 1, and the rest will be necessarily, because here we have exactly, 0. So it's enough to choose 4 digits between these 10 digits to determine the place of ones, okay? So how do we compute it? We have this combination, okay? So 10 choose 4 is this 210. So we have this many bit strings of length 10, which contain exactly 4 ones, okay? How do we compute it? We have 10 factorial in the numerator, and we subtract them. We have 10 minus 4 factorial times 4 factorial. So we get this. We rewrite this as in this form, and we simplify this and this one. So we get that. Okay, we have the final answer. What about this part? Now we want to find the number of these bit strings, which contain at most 4 ones. So it may either contain 4 ones, okay, or 3, or 2, or 1, or none, okay. So in order, we compute them and obtain this. Remember, 0 factorial is 1, so this is, for example, 10 factorial over 10 minus 0 factorial, which is 10 factorial, times 0 factorial, okay? So we simplify them. We have 1 over 0 factorial. By definition, okay, 0 factorial is 1, so we have 1, okay? Now, at least 4 ones, okay, at least 4 ones. So we can compute it now by this. We have 2 to the 10 many bit strings of length 10, okay? There is no condition for these bit strings, okay? In total, we have this many bit strings of length 10, okay? So we know that this is this many bit strings have at most 3 ones, right? Because here you see this, 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 and this. Sorry, okay. The sum of these numbers give us the number of bit strings that have at most 3 ones, right? 3, 2, 1, and 0. So how do we compute it? We know already this combination, okay? It's 210. So we subtract them and get this. So we have this many bit strings that have at most 3 ones. If we subtract them, we had 2 to the 10 many bit strings in total, okay? And we have this many bit strings that have at most 3 ones. Okay, so we have this number, which contains the bit strings of length 10 that have at least 4 ones. Now we want to compute the bit strings of length 10 that contain an equal number of zeros and ones. So how do we compute it? We have 10 digits, right? if we want them to be equal numbers, so there should be 5 many zeros and 5 many ones. So it's enough to choose one of them. So 10 choose 5 give us the desired number, which is this. Okay, so we choose 5 digits and we put them zeros, for example, and the rest will be already ones, so we don't have to compute another thing. Okay, so we have already this number. Now we have a group which contains n many men and n women. Okay, now we want to find the number of arrangements, okay, such that in this row, in this arrangements, men and women can alternate. Okay, so if we see a woman, we see next to her a man. If we see a man, we need to see next to him a woman. Okay, so we want such arrangements. Okay, so for example, we start with the woman. Okay, so we have n many people who are women. So we know they may be arranged n factorial, okay, in many ways. So similarly, men can be also arranged n factorial in many ways. So it's not done yet. We arrange woman. Okay, so then we arranged men. Now what do we do? If we multiply them, will be found the total number for this one. Okay, but remember this arrangement, for example, start with woman. It may start with a man, right? So again, we have n factorial times n factorial, many ways to arrange them. Thus, for each one, we have n factorial squared many ways, okay, as arrangements, as the number of arrangements. So we have, in total, this many arrangements. Okay. Now we have a coin which is flipped 10 times, okay. We can flip it either heads or tails. So we want to find the number of outcomes, okay, that are in total. First we compute it. So for each flip, it's like the bit strings. For each flip, we have two choices. We have two possibilities or two outcomes. One of them is heads and the other one is tails. So we have 2 to the 10 many outcomes, right? As we flip 10 times, we have 2 to the 10 many outcomes. Now for B, we want to find the number of outcomes that contain exactly 2 heads. As we did that before, it's enough to choose, okay, 2 of them, okay, to flip from out of 10, okay. So we compute this 10 choose 2, okay, the combination. So we get this numbers. Now we want to compute the number of these outcomes that contain at most 3 tails. So there may be 0 tails, okay. There may be none of tails, 1 tail, 2 or 3, right? We have at most 3. So we compute each of them and add to find the total numbers, okay. For the last part, now we have to compute the outcomes, the number of outcomes that contain the same number of heads and tails as exactly as in the bit strings. We compute this because there are 10 many flips, right? So 5 of them should be heads and 5 of them should be tails. So it's enough to find only one of them, okay? Because the rest will be the other. So We have this number. Now we have a bagel shop now, okay, which has some types of bagels, okay. Here we have, wait a minute. So here we have this, 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 that. Okay, we have 8 types of bagels. Okay, so we have 8 types of bagels. Now, how many ways are there to choose 6 bagels? So, remember, we have 8 many types, but these 6 bagels, each of them, actually all bagels that we will choose can be of the same type. So each of them can be, for example, plain bagels, or they all of them can be egg bagels. So that's why we cannot do this. We cannot compute this, because in here we have one many choice for each type of bagels. Okay, this is not correct. That's why this is not correct. For example, if we choose 6 bagels, uh, such that all of them plain bagels, here we have 8 types. One of them is plain, right? One of them is plain bagels, and the other ones, for example, this raisin, salty, egg, okay, the other ones. But for these 6 bagels, we can, if we do this, if we compute this combination, we can, for 6 ones, we can choose only one plain bagel, okay? To not have this, okay, we add 5 many, for example, bagels, 5 many types. You can think of like this, okay, 5 many other types, okay. This is not valid for only a plain one. This is valid for all the other types of bagels, okay. So to choose like this, okay, to be able to choose of the same type for each bagel, we add 5. We had 8 types and we had 5, okay. So we get 13. Now we compute 13 choose 6, which is this, okay. I hope you understood. So now we want to choose a dozen bagels. So we want to choose 12 bagels actually. They're the same meanings. So what do we do now? Remember, we had 8 types of bagels, right? So for example, again, if we want to choose 12 bagels as all of them is plain, what do? We need to add 12 because we had one before in the 8 many types, okay? We need to add 11 to have 12 plain bagels, for example. The type of the bagel was plain was just an example. For each one, we need to have a choice, okay, for each 12 bagels, okay, for each these bagels, we need to have a choice to choose the same type, okay. That's why we add 11 here. So we had before 8 types. 8 plus 11, we get 19, okay. How many bagels do we choose? We choose 12 bagels. So we compute this combination and get this number. What about this? 2 dozen, which means 24, right? Again, we had before 8 types. Now we add 23, so we get this 31. Okay, and we choose 24 among them, so we get this number. In the exam, you don't have to compute these ones if you don't have a calculator, so uh, don't you mind these ones, okay? It's enough to write that part of me. Now, what about this? A dozen bagels with at least one of each kind. Now, we want to select 12 bagels, okay, a dozen bagels, with at least one of each kind. So, remember, we had 8 types, okay? Now, it's just enough to determine the remaining 4 bagels, okay? Because for each type, we need to have a bagel. So we had 8 types now, and we had to choose 12 bagels. So we have now 4 bagels. These 4 bagels can have any type of the bagels, okay? So how many types we had? We had 8, but these 4 bagels can be, for example, all of them can be plain again. So we need to add 3 as we did there before. Because why do we add 3 for these 4 bagels? Because here 8 contains only one plain. You can think of like this. Here, these 8 types, uh, we have plain, raisin, remember, egg, right, salty, right? These 8 types of bagels we had, right? For each type, you can think we have one choice in here, okay? For each type, we have one representation, okay? But here we have 4 bagels, so we need to add 3 to be able to choose again and again of the same type, okay? So we have 11, choose 4. Now a dozen bagels with at least 3 egg bagels and no more than 2 salty bagels. Now this is fixed, at least 3 egg bagels and no more than 2 salty bagels. We need to examine the cases. So for the first case, we have at least 3 egg bagels and no salty bagel, okay? We will not choose salty bagel. So we had 8 many types before and we subtract this one, okay, it's the salty bagel. So we have now 7 types, okay? And we want to choose dozen bagels, okay? And at least 3 of them will be egg bagels, so we have 9 left, okay? 9 bagels left because 3 of them should be already egg bagels, okay? As we have here at least. So we have 9 bagels now. We had 7 types. Still, we cannot choose salty bagel, okay? That's why we have 7 types now. But for these 9 bagels, we can choose the same type for each one, okay? So we add 8 here because one of them is in there already. For the for the remaining 8 ones, we add 8 here and we choose 9 bagels, okay? So we have this combination. What about this case? Now again, at least 3 egg bagels. We have again 9 bagels left because 3 of them will be egg bagels and 1 salty bagel. So one of them, okay, as in here, will be salty. So we have 8 bagels now. But this 8 bagels cannot be salty. This is fixed, okay? This is fixed. 1 salty bagel, only 1 salty bagel. So we have 7 many types again. That's why we have 7 many types still. So we add 7 because we need to choose 8 bagels and each of them again can be of the same type. So that's why we add 7 here. So we have this combination. And for that, we have egg bagels, 3 egg bagels at least, and 2 salty bagels. So again, we have 9 bagels because 3 of them will be egg bagels necessarily, and 2 salty bagels. So we have now 7 bagels. We had 7 types again. Okay, these ones cannot be salty either. So we have 7 types of bagels. Okay, so we add 6 because again, by the same reason, they can be of the same type. So we add 6. Okay, so we have this combination. Now in total, we add these numbers and get this number. So we have this many bagels, at least 3 of them egg bagels and no more than 2 salty bagels. Now we have this equation, okay, this equality. We will find the number of solutions such that these xi's, these variables, are non-negative. Okay, this part is important. Now, I started with a basic example here. So here we have this equation for this part. First, let's see what happens here, then deal with that. So if we have this equation, for example, for this solution, 1, 0, 4, we'll denote it by this little o's, okay? So, for example, what does that mean? If we put these 2 dots or blocks together, so the left of this, let me write it clearly. The left of this block, we have 1 dot, empty dot, right? So x1 is 1. So between these 2 blocks, there are no empty dot. So we have 0 as the solution of x2. And to the right of this block, we have 4 empty dots. Okay, so x3 is 3. So how can we choose such solutions? We have 7 many empty dots at first. Okay, think like these ones also empty dots at the beginning. So we have 7 many empty dots, and we just choose 2 of them to determine the values of these variables. Okay, so we have this combination. Again, also, for example, for this solution, we can also determine it or denote it by using these ones. So first we have the dot, this dot here, block, or so we have 0 as x1, and between these 2 dots we have 2 empty blocks, so we get 2 for x2. And on the left, on the right, we have 3. So we have this. Again, among 7 empty dots, we choose 2 of them. So here we had 3 variables, and we choose 2 of them. Actually, 2 blocks, right? We choose 2 blocks when we had 3 variables. Okay. Now, what do we do for this our question? We want x1 to be greater than 1 or equal to 1. Okay. Now, remember, we want solutions that are non-negative, sorry. So that's why we let x1 prime to be this, x1 minus 1, to have some number which is non-negative, okay? So now we have this equation. Here we have this equation. So remember, here we had 21, but instead of x1, we wrote x1 minus 1. So instead of 21, we have 20. Now what do? We will choose 4 blocks, okay? As we have 5 variables, we choose 4 blocks. Remember, we had 3 variables, we chose 2 blocks. Okay, so the number of variables -1 gives us the blocks the number of the blocks. So here we have 4 blocks. We need to choose 4 blocks among 20 plus 4 zeros. Okay, here we had 5 as in on the right of the equality, and here we have 7. 5 plus 2. Actually, it's 5 plus 2, but that 2 is the same with this one. Okay, the number of the blocks. So here we have 4 blocks, and here we have 20. 20 plus 4 gives 24. So we have 24, choose 4. Here we have the solution, the answer. And what about this one? We want each variable to be greater than or equal to 2. Okay, so we write each of them as in this form, xi prime. We let it to be this xi minus 2, where I is I takes values from this, from 1 to 5. Okay, so here we have this equation now. We know x1 prime is x1 minus 2, and for each one we write the definition of these variables. So we have this 21 minus 10. Okay, we have 5 minus 1 minus 2, sorry. So we have this 11. Remember, we have 5 variables, so we need to pick 4 blocks, okay, among 11 plus 4 zeros or empty blocks. Okay, so we have this combination. Now we have this condition. So if there was no restriction, the number is this, right? So we had 21 here. We need to pick 4 blocks. So we have 21 plus 4, which is 25. Okay, 4 blocks. So we have this number if there was no restriction. If we have this restriction, then what do we have? We just plug this one into the equation, into the given equation. So we have this, okay? Now we have 10 plus 4 blocks, so we have this 14, and we pick 4 of them, so we get that, okay? If the restriction was this. Now what do? We subtract them to get this condition, okay? So we have this number. What do we do now? We have these conditions. So to obtain this situation, we compute these ones, okay? So for A, first we need to compute this number, okay? Where x2 is greater than 1, greater than or equal to 1, and x3 greater than or equal to 15. First we compute this, then this condition, then this, and finally we'll have this d, the number d, which gives us exactly what we want here. So for A, the number of solutions where x2 is greater than 1 and x3 is greater than 15, we plug these ones again into the equation and get this number 5. So 5 plus 4 gives us 9. So we have 9 many these blocks, empty blocks, and we choose 4 of them. So we have this. And for B, we have these ones. For each one, we have these numbers which are non-negative. Okay, So we have this one, we add 4 again because we'll choose 4 blocks. So we have 5. Now we get this combination. And similarly, we find C, the number, okay, and D is this, which gives what we wanted. Now for this question, we want to find the number of the strings, okay, which can be made by these letters, okay, but we need to use all letters, okay. So here we have 11 letters. If we had different letters, okay, we have exactly 11 letters, different letters. We would arrange them 11 factorial many ways, okay, different ways. Now, as we have repetitions for these letters, okay, B, A, and R, we compute it by this formula. You can say a formula to that. So normally in general, we compute by this if we had different letters, 11 factorial. As we have repetitions here, we divide them, okay, we divide it by 5 factorial, 2 factorial, and 2 factorial. This 5 for A, this 2 for B, and this 2 for R, okay. So we have this. Now again, we want to compute the number of strings, okay, which can be made by this word, the letters of this word. Okay, now we again use all letters, but our condition here is this. We want all 3 A's to be consecutive, okay? So as we have this condition, we can think these 3 A's as a letter, only one letter, okay? Now how many letters we have? We have 2 R's, 1 D, 1 V, 1 K, and one letter as which seems like this, okay? So we have 6 letters, okay? We have 6 factorial many ways. But remark that we have a repetition here. We divide it by 2 factorial, so we get this number, okay? So that was the last question. If you have any question, except these ones or again these ones, okay, also you can attend the office hour, which is on Fridays between 5 and 7 p.m. So see you there.